Okay, this is Fluid Mechanics, third lecture, chapter 4. So we just talked about office hours, right? And then, I guess before that, I had a lot of emails. Some people were gonna miss class today, they weren't feeling well or missing quizzes. Just to be fair, that's why we are dropping the lowest quiz score, your lowest quiz score at the end of the quarter. So if people are sick, they might miss one. It doesn't penalize the people for being here. Then I don't have to, evaluate each request. So lowest quiz score is dropped for people watching at home. And yeah, if you guys happen to miss class, I try to record them. Not the best quality, so I still recommend showing up. Okay, and then we're gonna talk about the lectures I posted. You guys see those, hopefully? Okay, the modules page, the YouTube link for some reason wasn't working too well. I don't know if you guys have seen that. So I posted them in announcements. Can you guys see them at the module level? Does anyone know? Nods? Okay, awesome. So I posted them in announcements too. If you happen to not have it, my YouTube channel's on just my first and last name. You'll see the lectures there if you don't see them. And they're on Panopto if I record them at home, but these will just be on YouTube. Okay, so we're gonna quickly review what we discussed on Bernoulli's derivations. And I just recorded that because I posted it, I think, Saturday night or something. So in case you didn't watch it yet, it's not the end of the world. You'll still kind of understand what's going on. And you can watch it afterwards. It's just the derivations of how we got the equation. So, and we're going to also bring up assumptions we use for Bernoulli's equation, because I actually did not put that in the lecture video. Continuity equation, which I mentioned, but we're going to go into more depth about that. And we're gonna do, I think, 2 to 3 examples. And I promise you now, Bernoulli's equation is gonna be on your exam, probably for both of them. Okay, this is huge for fluids. So yeah, this is big. So that's gonna be on there. And then you have one of your homeworks, which I already posted. There's gonna be a problem that's not Bernoulli's equation, which is just your Newton's second law applied to a streamline in the normal direction. And I'm gonna go over what equation you're gonna use for that. And then you should have everything you need to do your homework 2, which I already posted. And then quiz at the end. It's one question, 15 minutes. Well, we'll see. I think I might have made it too easy, but we'll see. But I thought I'd give you guys the benefit of the doubt because last week's lecture was online, and that's what it's kind of about, right? Chapters 1 and 2. So. And I'm a reasonable person, right? If everyone's not doing well on the quizzes, I will do something about it, okay? So I think that's about it. Any questions before we dive in? Yes?
When is the next quiz?
Yes, next quiz is going to be next Wednesday, I believe, because Monday is MLK Day, right? So you guys have off. And I believe I might have structured the class so there's probably no recordings and stuff. So we'll see. I'll check the schedule. There might be a recording. If it is, it'll be quick. But yeah, no class Monday. Next quiz will be next Wednesday. And that will be on what we're learning today, Bernoulli stuff. So, okay, any questions? Good. Okay, and I think we have more students now because they're shifting from other section to this one. So just a heads up. Okay, so I'm going to breeze through what I talked about in the video. If you haven't watched it, I'd say just watch it. So these are streamlines, right? So essentially, this is the figure of a streamline. They're lines tangent to the velocity vector, which is this v, okay? And this is the graph of the streamline in the z-x plane. And these are all the variables defined, okay? And the only reason why this is up here is to derive Bernoulli's equation. Okay, this is the free body. I went into depth. I'm not gonna go do it again. So this is just deriving, bang, important equation. Okay, so that's important. Okay, so this is what we derived along a constant streamline. Okay, these are the variables, right? Pressure, density, velocity, specific weight, and height. And the majority of the time, even though we derived it using the constant streamline, we'll be using this form of Bernoulli's equation. And is essentially you're taking a point of one particular point in your fluid or liquid in a first position and then a second position. Okay, so we skip the derivation. This is the equation. Any questions on derivation? I don't know if you guys are big into derivations, but yeah, I know some people, the majority of my cohorts, when I was going to school, they just wanted this. But my teachers back then, they would just explain how they got there, and then just so you guys have a background of how. So this came from Newton's second law. Okay, this was not in the video. These are assumptions you have to use and do when you're using Bernoulli's equation. So they have viscous effects are assumed negligible. So that means you're not accounting for the viscosity of your liquid or fluid, which means no shear stress, right? Flow is steady. So this particularly means velocity, pressure, and density. When you measure at one point of the fluid, it is constant. Okay, so you'll see in our problems when we work on today, it'll be like, take a position of this location here, find the pressure, density, or velocity. You're just assuming these properties are constant at that position. And then flow is incompressible, which means density does not change, which is probably going to be the same for all our problems, right? Because our rho is a single value, it doesn't change at all. And this is applicable along a streamline because that's how we derive the equation. So like I said, if you had homework, these are what you would list if you use this equation, right? You had your given, finds, and assume, like Dr. Bridge would show you. You would assume these and you'd write it down, and then you'd continue solving. Any questions? Awesome. Okay, so we're gonna dive right into it. We have about 3 examples to get through. And then we're gonna do one derivation at the end and then a quiz. So let's read this problem. Okay, water is siphoned from a large tank's right there, and discharges into the atmosphere through a 2-inch diameter tube, as shown below, which is there. Okay, water is siphoned from a large tank and discharged into the atmosphere, which is there. Okay, so now what we want to do is find the exit velocity of the tube at point 2. So when I said steady flow, right, this point 1 and point 2, we're assuming those properties do not change at those locations. I think I said in the previous lecture before, this triangle, this means that's the surface of the water. So the rest is atmosphere. And that's a big hint to these problems when you have your liquid exposed to atmosphere or just your air. The pressure is going to be 0 there because we're using gauge and not absolute. Okay? Okay. So you guys can, oh, these are also posted on Canvas, so you don't have to rewrite or anything. So let's write Bernoulli's equation. Actually, I can go all the way here. So P1 gamma. Okay, so this is your Bernoulli's. If you're stuck on a test exam, just start with this and solve as you go. So first thing we start off with is, like I said, if these are exposed to your atmosphere, your air, pressure is going to be 0. The only times you'll have a pressure usually will be given if it's an enclosed container, and it'll give you the pressure there. So just because of this picture, right, the location at 1, location at 2, pressure is gonna equal 0 there. Okay, so right up here, P1 equals P2 equals 0. Okay, so that means this is gonna be 0, 0, right? And then when your fluid is static like this at the surface, this is also going to be 0. Okay, so this is moving down here, and that's what we're solving for. So this is going to be 0 right here. Okay. Okay, so V1, 0. Guess this whole term is gone, so. Okay. Any questions so far? Not too bad, right? Okay. Now we just do our algebra. So we're going to get what, Z1 equals V2 squared divided by 2G plus Z2. And then, what are we solving for? We're solving for exit velocity, right? So that means we're going to solve for V2. Okay, so that means we're going to move this over here. We're going to have Z1 minus Z2, Z1 minus Z2. Okay, divide this. Oh, sorry. Z1, Z2. Okay, multiply this by 2G. Square rooted, right? Make this guy smaller. Okay, so make sure I have my algebra right. Z1, Z2, 2G, square rooted. Okay. Anyone have a calculator on them? This fast? Let's see, I'll let you guys compute it. And remember, the distance is from point 1 to point 2. So that's going to be 9 plus 3. And here's a big thing that I learned from physics, my physics 1 and 3 professor. If you can, every time you write a number, write a unit. That's just going to help you in the long run. Okay, so 9 plus 3, this is feet. Oh, let's do 9 feet plus 3 feet times 2. Then we're going to do 32.2, right? Okay. Okay, dimensional analysis works out right. This is feet times feet, feet squared, divided by seconds squared, square rooted, that's going to be feet per second, which is your velocity. Anyone have an answer? 27.8, 27.8, yes, beautiful. Thank you. Feet per second. Okay. Any question? Yes?
Can you explain again how the Z value works for 9 feet and 3 feet?
Yep, so when you do your Bernoulli's equation, you have your location 1, then location 2. So this is essentially what it is, point 1, point 2.
So Z1 is 9 feet, and then Z2 is 3 feet?
Right, that is true. So they should be added. Z1.
Maybe it should be subtracted.
No, they should be subtracted.
Z1 minus Z2, so. Where are we setting 0?
Yeah,
Sorry.
your datum, I'm pretty sure, is at the bottom of the tank.
Correct, yeah, so
If we're setting 0 at the bottom of the tank, then it would be negative 3 feet, right? Which is what
Yep.
I think you did.
right, so
If we set the
Good point.
bottom at like 0.2, then it would still be 12, because 0.1 would be 12 feet, and 0.2 would be 0.
okay, perfect point. Thank you. Was that Ben? What was your name again?
Ryan?
Ryan. Thank you, Ryan. So yeah, we're setting this at 0 here then. So you add these two. So yeah, we can call datum, assume z equals 0 at 2. So actually, no. Let's set it to 1. That makes more sense. Because if you set it to 1, it would be because it still needs to be the distance difference there. Sorry, 1 second. Let me make sure that's just right up here. z1 minus z2. Because that needs to be 12.
Yeah, so you're subtracting z1 and z2, and it's 9 minus negative 3. If we put the
Right.
down, so it'd just be 9 plus 3, kind of what you had.
Right. 9 minus negative. So you're saying you'd set your datum here then, right?
Yeah, I was going to say, I think it's assumed by what we had on the board that the datum was where you kind of said.
Right. Okay. Thank you for, I should have clarified that. Okay, datum's right here. So datum is at, yeah, so you can set them wherever. You're going to get the same answer, right? So if you set it here, you're going to have 2 positive values, and this is going to change. If you set it up here, you're going to have 2 negative values. This is going to change. So I guess for my solution to work up here, datum's going to be at this red line, or point of 0, right, which is 0 height. Okay. We'll do assume. Say red line. Okay, yeah, so that'll be 9 minus negative 3. 12. Thank you. So maybe for exam, that's a good point. I will, if I don't define where you should do it, just kind of, well, I'll be able to tell from your solution where you set it to. So, okay, any other questions on this? Good. Okay. So people at home, I might take a picture and post this for them. And then I'll update the slides and I'll put that in there. Okay. Now we're going to talk about the continuity equation. So I talked about this in the lecture video, and this is important because when you're missing variables in your Bernoulli's equation, you're going to be, this is going to be your first go-to basically, okay? So just a quick reminder, mass flow rate, defined as m dot, is basically your mass with respect to time. And so I boxed this one because that's what the textbook does. I would write all of this. It's on here though. This is going to be good for your equation sheet because sometimes you'll need the Q, sometimes you'll need the mass flow rate, okay? So volume flow rate, Q equals mass flow rate divided by density. And if you do the dimensional analysis, you'll get your volume divided by time or seconds. So this is equivalent to volume flow rate equals velocity times the area. And then if you do some substitutions here, right, you move rho over there. Right, so you have your mass flow rate is equal to rho times velocity times area. This is also an important equation here. And the majority of the time, you're going to assume this mass flow rate 1 equals mass flow rate 2. And if you substitute everything in, you'll get this here. But most of the time, right, our fluid's incompressible, so density does not change. So these densities will cancel out, and you have this equation down here. And I have a figure kind of showing how this looks like. Looks good. Okay, so intuitively, so you understand what this equation means, don't even look at what I have there. Think of a hose, right? So if everyone uses a hose at any point, wash your car or your plants, the moment you put like your thumb on like the hole, right, the pressure increases. So this is kind of a good visualization of a bigger area down here and smaller area up there. So area 1 and there's area 2. So you see 2 times area 2 is area 1. And velocities in and then out. If you solve all of this and put that into there, you're going to get A1 V1 equals A2 V2. So the volume flow rate is equal on both ends of this nozzle, you can say. Okay, so like I said, 1's location of inlet, 2 is location of outlet, and velocity increases once the area gets smaller, right? Just like you're washing something, close the hole, right? Pressure increases. So. And that's all that equation is talking about. Any questions about that? Okay, good one to have on your equation sheet. Okay, so now we're going to go back to the same exact problem, and we're going to determine the volume flow rate of the tank, which is Q, right? So, marker. I'll leave this up here, then I'll do the other part of it here. So volume flow rate, we want to find Q, right? And then what we have was Q is equal to V times A. Okay, so that's pretty simple, right? So we have our velocity already over there. A is equal to pi r squared. Right, if you do d divided by 2, because we have diameter, right? Yeah, we have diameter, so squared. That's equal to d squared over 4 pi. So your area is equal to this. Right, just area of your circle, and then you have your V already. Yeah, that's pretty much it already for this. Someone want to plug that in and give me an answer for that? V is right there. This is feet per second times feet squared. So final answer will be feet cubes per second. Any answers? If not, that's okay. I will just say it. You got to do dimensional analysis though, right? Because this is in inches. I'll write it out while you guys work on it. Yep, feet cubed per second. So you probably did dimensional analysis already. You converted the inches to feet. So perfect. Awesome. I got 607. Oh, 6-1, same thing. Or not same, but you know what I mean. Yep. Okay. Box. Good. Any questions? I'll take a picture for people at home. Okay, we're doing good on time because I want to give you guys more time on your quiz. Okay, so I'll post that picture onto this slide and post the updated slides. And like I said, the reason why I do this too is because when I used to watch lectures, I like to just sit back and watch. Taking notes is important too, but I retain more information just listening. So if you guys happen to not take notes at all, it'll be there probably. So, okay. This is going to be our last example. And the way I kind of chose this is because our first example was just Bernoulli's equation without the continuity equation, right? We just solved for it over there. And then you had to use your continuity equation to find the volume flow rate. So that combines both of the equations we learned. So this problem is going to use both. Okay, so you guys can get a head start and read it. I'm going to erase this unless somebody else needs it, and we'll solve it on this side. Okay. Okay. Okay, so we are given a stream of refreshing beverage of diameter, so little d of 0.01 meters, flows steadily from the cooler of diameter big D, which is here. This is the cooler, little d is down here, of 0.2 meters as shown. Determine the flow rate Q from the bottle into the cooler at a depth of the beverage in the cooler is to remain constant at H equals 20, or 0.2, right here. Okay. So, right, if you had this homework problem, given finds assume. On exams, I know how exams are, right? You're just really just thinking you had to get the number out. So I won't probably knock you down if you don't write your given finds and assumes, but your solution is going to be graded fairly on this. So, okay. So we'll start off with Bernoulli's equation. P1 plus 1 half. And I don't know if you already noticed when I write my specific weight on the other side, if the fluid's not changing, those usually don't matter too much, right? So P2 plus 1 half. I guess if you have to change your heights, you have to factor them out. But okay, so what we have to do first is find our assumptions, right, of what's 0 or not, because there's too many variables over here for us to solve. Just looking at this picture, does anyone want to give me something that might equal 0?
Since it's an open container, would pressure be 0?
Yep. Which one? 1 or 2?
I think all across, right?
Yeah, perfect. Awesome. Have another one over here? Thank you. Awesome. So we're going to have P1 equals P2 equals 0. Okay. Alrighty. Any other assumption that we can make? This one's a little tricky. For your velocity 1, should that be 0 or not? Someone can just guess too. That doesn't hurt.
Maybe not, since the height shouldn't be changing.
Right, so it's not 0. So yeah, height doesn't change, but also another thing is, you can see just by the picture, while water's flowing into this is a little bit moving, right? It's not just static. So our V1 will still have a value. Compared to the other problem, right, it was just static on the surface. Okay, we're gonna make,
Can you assume that the density is constant throughout?
yes. Yes.
Is that going to simplify our time?
Yep, that is true. So we'll leave it in there, but yeah, since right here to be incompressible flow, density is constant. Good point. Yep. Okay, so here we're going to set our datum now. So I'm going to make my Z2 equal to 0. And then my Z1 is going to equal H. Okay, so that way we don't have that confusion we had earlier. Okay, so I think that's all our assumptions. We'll start getting rid of some stuff. Okay, so we have pressure 1, pressure 2. Z2 is equal to 0. That can go away. And what are we solving for again? Volumetric flow rate, right? And that's Q is equal to VA. And let's see which Q they need. Determine the volume flow rate from the bottle into the cooler. So we need V, right? We don't have V. We have A from the dimensions. Okay, so for people watching at home, we're going to use this equation here. Oh. Okay, so let's just work this out. 1/2. Squared, and then I guess we can solve this in terms of V1, V2. Let's just keep this now and let's dive into our continuity equation, right? So you have Q1 is equal to Q2. So that's equals to A1 V1 equals A2 V2. Okay, so we already defined our area equation over there, right? Pi d squared divided by 4. So we're going to have pi 4 big D squared V1 equals okay. So now let's go back to this equation and check what we have and what we don't have, okay? So density of water, we have that from our tables. And then height Z we have, specific weight we have from tables. So the only problem now is V1 and V2. And it looks like, sorry if I'm blocking your way here. It looks like we cannot find our velocity from what we have there right now, right? From the givens at least, it's not there. So let's solve, you can either solve V1 or V2 and plug it in. I'm just gonna solve for V1 and plug this into here. Okay, so we're gonna get V1, so this cancels, V1 is equal to D1 squared, V2. Oh, sorry, V1, D1 squared, V2 by D squared. Okay, V1 equals D1 squared, V2 divided by big D squared. Here's a better way of looking at it, I guess. Simplify even more. What do they call that? Sorry, let's little d, not D1. D1 dt squared V2. Okay. I'm going to erase this. I'm going to rewrite our V1 equation up here. Okay, so why do I keep writing D1? Okay, we're going to erase this. Let's erase this here. We'll just solve it as is. So sometimes you can skip a step, and you can just, since, like someone mentioned previously, since density is the same and specific weight is the same, you can just kind of pull those out. But we're just going to solve this as is here. So let's solve for V2. Okay. Actually, let's make it easier on ourselves, and let's take these out now. So if these are constant, right, you can actually take rho out, specific weight out, because these are constants. So now you're going to be left with okay. Well, this is right, so specific weight is gravity times the rho. So all of these have rho. You can take those out. Z1 times G. Okay, so I just factored out all the densities and canceled them out. Now let's solve for V2. So V2 is equal to this times 2. So we're going to have, see if I did that right. V2, I did not square root it yet. V2 equals times 2, 2G1Z. Okay. Square rooted. I'm going to make that neater. Okay. Then we have V1 here. Oh, sorry. I should have not done this yet. Let's put this in first, V1. So, okay, 1/2 V1. So D divided by D squared plus GZ1 equals 1/2 V2 squared. Okay, so this is squared. This is technically to the 4th power. Oh, sorry, this is squared again, so to the 4th. Okay, so let's simplify this. Okay, that looks right. Okay, so now we solve for V2 now. Here we go. V2 equals 2, so we're going to have D to the 4. You guys are probably ahead of me already.
Is there supposed to be a V2 in the brackets? The first one?
For which part?
For the bracket.
Or you substitute V1 squared right there, yeah.
Oh, thank you. Forgot that. So V1 squared. So this is going to be V1 squared here. Thank you. Okay. So looks good now? Looks good? Sorry, I forgot about that. Thanks for pointing that out. Oh, right, V2 squared. Sorry. Okay, looks good now? Okay, all right. Let's move. You can do it whichever way you want. Let's move this guy here. Have V2 squared. Okay, so now we factor out V2. I'm gonna switch these in my head, but you'll see what I'm saying. So V2 squared minus let's make sure that's right. We have, move there, V2 squared is out. 1/2 minus 1/2 d d4. Parentheses here. Okay, so you guys see it, right? It's just going to be this whole term divided by this square rooted. Sorry for the mess. I'm going to write that over here so people can see. Okay, so, all right, yeah, let's move it here. So you're going to get V2 is equal to GZ1 divided by d to the 4, okay, square rooted. GZ1, 1/2 minus, okay, square rooted. That's the variable form. And I hope you guys still do the same. When I went to school, it's all variable form first and you plug it in at the end. A little bit cleaner too, right? Okay, so here's your V2. And I will tell you the answer. I will not make you guys type that in now. Okay, so you'll get 1.98 meters per second squared. Okay, so then now that we have our V2, last easy step, anyone tell me how we get the volume flow rate?
You just multiply it by the area at function.
Perfect, thank you, exactly. So, right, we have our equation of A is equal to, what do we have over there? Pi d squared over 4. And we're using little d, right? Yep. Okay, Q equal to V2, A2. You're gonna get okay, so that's how we combine the continuity equation with Bernoulli's. Ooh, take a picture. Ooh, it's not a good picture. Okay, let's see. So we are 10 minutes away from our 1 hour mark. Okay, any questions before we move past that? This might be an older edition of the textbook. So their solution might be different, but it should come out to the same. And yeah.
So did we solve for the flow rate from the bottle into the cooler or from the cooler out?
From out, because there's going to be Q1, Q2. We solve for Q2.
Yeah.
Yep. So
The original question was from the bottle into the cooler, so I was just confused.
oh, you're right. Well, Q1 is equal to Q2, right? So they would be the same. Right. So they're going to be the same. So yeah, they could be Q2 here. Good point. Good question. Good question. These questions are awesome because someone probably has them too, right? And we can clarify for everybody. So good, good. Okay, so what to look for Bernoulli problems, right? Kind of like we talked about is pressure is exposed to atmosphere, they usually equal 0. Static fluid means the velocity. So I'm really careful with my wording here. I said could, right? Most of the time it's going to be like that, but sometimes it's not. You'll find a problem that doesn't. Most of the time it's going to equal 0, velocity equals 0. And then if you do not have, right, if you're missing variables, use your continuity equation. And since you guys are here, I'm kind of working on writing the exams already. I'm not sure if I'm going to put it on there yet, but there is another good problem where you have a missing variable and then you have to use the ideal gas law, which we reviewed first day, right? And that has the same variables of that. So maybe for an exam, I might do something like that. So it'll be something Bernoulli's. You're missing variables. Could be continuity equation, could be ideal gas law. Which is essentially the same thing we're doing, right? You have your missing, then you're going to have to use a different equation to do it. Okay, question? Yep.
A static fluid is denoted by the lines on the surface, right?
The lines.
Like on the previous problem.
Yep. Yeah, so.
No, the one we did before this.
Yep. Free surface with the triangle.
Denote a static fluid.
Yes, free surface, what they call in the textbook, I think. Free surface, yep. Okay. Okay. Okay, see how we're doing on time. Trying to think we should take a break first before we go through this derivation. Okay, how about, is everyone okay? We power through this derivation. We'll take a break, quiz, and leave early, depending how fast you do the quiz. Okay, is that okay with everybody? Okay, perfect. So, in my previous lecture video, we did Newton's second law along the streamline in the S direction. Okay, so quick review. Like I said, this is good to know. But at the end of the day, I'll give you the equation, and that's what you're going to put in your equation sheet, and that's what we're going to use to solve problems. So I think like a student too, but this is how we get there. Okay, so S direction, it's at an angle, so streamline directions for S, normal directions in N. So what we do here, last lecture, we did the sum of forces in the S direction, and we got Bernoulli's equation, right? So now we're going to sum the forces in the N direction, and then we're going to get a different equation that defines a pressure gradient. And you're going to do that for the first homework problem that I already posted. And I wanted to give you this because I hate having homework, and like professor didn't even talk about that in class, right? So this is me talking about it. And then everything else is Bernoulli's after this. So what else should I review, right? So shear is equal to 0. Delta S, delta N, this is how your fluid particle is changing. In the last lecture, Y is the thickness of the particle coming out of the page, but I do not think we need that here. But if they do, delta Y is we will. So delta Y is here. That's delta Y in and out of the page. You have your angle. This is your weight with your trig for your weight. And I will have this copy and paste it on the right here, and you'll see the derivation. Okay, so if you remember from physics 2, there's an equation for centripetal acceleration. It's v squared over r, right? A equals v squared over r. For anyone that remembers, sorry, that should be physics 1, actually, physics 1. So that's what we're doing because that's essentially your particle of your fluid along a radius or curve. You're going to have centripetal acceleration, right? So F equals ma. Your a is v squared over r from physics 1. Your mass is delta. And we're always having delta because your fluid's changing, right? So you don't have a solid mass exactly. N is in the n direction, which I explained here, n, right? So delta m from last lecture can be substituted as rho times change in volume. I mentioned this in the last lecture too. The cross out in the v is for volume, so you don't confuse it with velocity. So before we sum forces, this is your ma in your F equals ma. Okay? Nice? Good? Okay. So now what we're going to do, we have it up there again. We're going to sum our forces, right, and find them out. So let's find our weight, which is right here. Okay, to get the weight, it's the cosine, right? So adjacent over hypotenuse, right? It's right here. So you get this term going this direction. And then you can substitute weight with specific weight times your change in volume. So if you do the dimensional analysis, it's going to be equivalent. And then now, once you have the weight, you're going to do these two other forces here. That's going to sum the forces in, we call it here Pn, which is your pressure force in the normal direction. Okay, so let's just match them, right? So this term here is right here, right? Going in the positive direction of n, minus this term here, which is right there, negative direction. You simplify to this, more simplifications, and then you get to this here, which is your partial derivative change of pressure with respect to the n direction with your change of volume. Okay, so now what you're going to do is you add your weight force, which we got, and your net pressure force, which we just did here, and then you're going to sub them into here, and it simplifies to this. Okay. Okay, so now we set our sum of forces equal to ma, right? So remember, our ma is up here. Sum of forces that we just did is right here. And then you set them equal to each other. So then you just cancel out your delta v. From the free body diagram, cosine theta is equal to change in z over change in n. Right here. Adjacent over hypotenuse, change in z over change in n. So we sub that cosine in there. And then you get this, which is what you need for problem 1 of your homework. And in the textbook, they made another equation if you assume that the pressure gradient normal to streamline for in viscid flow with no gravity, you get this equation. And yeah, to be honest, I am just going off of section B's homeworks. So Dr. Abadi wrote these homeworks. So I go through them, make sure you guys have everything you need for the homeworks, and then I'll let you guys add it. So this is the one boxed in the textbook, but this is the one you're going to use for homework. Oh, perfect timing. Okay, any questions on this before we'll take a break and then do quiz and we'll wrap it up? Okay, awesome. I'll give you guys a break. And then one thing I remembered, just something weird about me. If you ever see me like looking at some of you and then I'm like moving my face to the side, I have one really strong eye and the other one's not, just my vision's bad. So I could use like a monocle and look like the Monopoly guy, but I don't. So I'm not trying to be weird and make people feel bad if I'm going like this. My left eye is a lot stronger than my right eye. It's my vision. Okay. All right, I will give you guys a break. If you have equation sheets, I will be looking at them. Maybe just have them in your desk in the front. Let's put all electronics away. You can have a calculator and your equation sheet, pencil, paper. I think you should only need 15 minutes to do this. Like I said, I think I might have made it a little too easy. We'll see. Then when you're done, you can leave. I will probably stay here for people who need more time. I'll be more strict on time on exams. So let's take a 10-minute break and meet back at 9:55. Oh, that's the end of the lecture. We're taking a quiz. Bye.